Good morning, everyone from Nigeria, and good afternoon in Bangkok. My name is Aliyu Muhammed Awwal. I will be sharing with you our work titled Inertia Type Projection Method for Solving Convex Constrained Monotone Nonlinear Equation with Application in Robotic Motion Control. So before I start, I would like to share with you this is my profile. These are my email for possible contact. And these are my area of specialization. This is where I'm currently working on. So let's start the talk. Our work has to do with iterative algorithm. And when we say iterative algorithm, we simply mean a mathematical procedure that uses some estimate of the solution. So using the estimate of the solution, we generate some sequence of points with the hope that those sequence of points will converge within the neighborhood of the solution. So when we have this type of situation, we call that method iterative algorithm. So the two figures here, the one from the left, it shows when you are given an initial guess here x1, then you will generate x2, x3, x4 until you have the exact solution. And iteratively, it's not always possible to get the exact solution. In some cases, you might get approximate solution. While this figure on the right here is showing when you are lucky to get a better initial guess, then it's possible you get to the solution faster. And when you have a very bad initial guess, then it will take longer time and sometimes it may not converge depending on the type of algorithm you are working on. So we need this definition. This is very familiar also. We need this in our algorithm. This is definition of a projection, which is given by 1. And this projection 1 here, it has these two very important properties, which we use in our analysis. Another definition we need in this talk is these two familiar definitions. That is, when a function, sorry, this is supposed to be omega from Rn to Rn, satisfying this inequality to we call it monotone. When satisfied this, then we say it is Lipschitzian. And we have some figure here. This is very familiar, so we don't need to waste time. So the problem at hand is problem 4. We need to find some point x hat in C, where C is a subset of Rn, such that this 4 holds. So when we have this, then we call it a nonlinear equation. And when this omega satisfies the inequality 2 here, then we call this problem a monotone nonlinear equation. And this problem 4 has a number of applications in signal processing, image, motion control, and what have you. Then this talk, the application we're going to discuss is the first one, which is robotic motion control. So algorithm for solving nonlinear system of equation is given by 5, where the way it works is when you are given xk, you are given alpha k, you are given dk, then we can compute xk plus 1. So we continue like that until it converges to solution. Where of course alpha k here is nothing but the step size, which we usually get it from either exact or inexact line search procedure. And of course, dk here is called search direction. In this talk, the search direction we are going to be dealing with, it will be computed using the spectral gradient-like method or the spectral conjugate gradient-like method, which is given by this. When you have x0, then you compute the direction using steeper descent, and subsequently you multiply it by alpha q. This alpha q is a real number, which will be updated in every iteration. While the spectral conjugate gradient-like method is a combination of spectral gradient and conjugate gradient. Many people in this forum are familiar with this. So the line search. Line search is simply a technique used to obtain the step size or a step length. So the step length, the aim here is to find a step length that will reduce the norm of the objective function, because we want to have omega of xk equal to 0. So by the time we start, it's possible we get a number not equal to 0. So we choose the steps as such that it keeps reducing. And remember, num is bounded below by 0. So eventually we are going to get 0 or a number very close to 0. So we have two types of lines which we can classify it into two. The first one is when we get the step size alpha k by solving this one-dimensional minimization problem, then we call this line search exact, and the alpha k that satisfies this or that is obtained using this called the optimal step size or step length. But if we cannot get this because it is very expensive, then we can impose some conditions such that that condition will guarantee this inequality. If we have this, then we call this approximate step size, and this procedure is called inexact line search. And in literature, you can find out that this inexact line search is the one people are using because it is less expensive and less cost. So what we are going to discuss has to do with inertial step. So this inertial step, the way it works, if we are given two initial guess, which we call x minus 1 and x0, then we can compute omega k here. So this omega k is what is called the inertial step. And this alpha k here is in this interval. In some cases, we may require that the limit converges to 0. So this inertial step has been incorporated in different types of algorithm, like variational inequality problem, split variational inclusion problem, and what have you. And it has been shown that incorporating this inertial effect into algorithm, it can improve the numerical performance. So following this, then this is our observation. This observation is from the previous presentation. So we said that time that to the best of our knowledge, we have not found anyone that incorporated the inertial step into derivative-free algorithm for solving nonlinear system of equation. So we asked this question: can the inertial effect speed up the numerical performance? So to answer those questions, we propose this algorithm 1 and 2 in the next slide. So this algorithm 1 and 2 is from our previous presentation because I need this so that I can show the improvement we have in this work. So given two initial guess, say x minus 1 and x0, then we compute the initial guess and we compute our search direction here. We observe that in the search direction, we have xk here minus omega k here, and we are using the image of xk and the image of omega k here. So which means this search direction is being computed using the difference between xk and the inertia and the difference between their images also. So this is what we use to compute the search direction, and we follow the procedure until step 5. So we continue like this until the tolerance here is satisfied, which is in step 1. So another algorithm, which is the algorithm 2, is this. So the difference between algorithm 1 and algorithm 2 lies in step 2, which is where to compute the search direction. If you look at the search direction given by 9 here also, it uses simply the difference between the xk and the inertial point and their images. So these two algorithms have been published in IEEE Access, I think last year. So this is the remark we have from algorithm 1 and 2. So the remark is algorithm 1 and 2 suggest that integrating inertial step into derivative-free algorithm could improve numerical performance. So, but as I said earlier, the search direction in algorithm 1 and algorithm 2 are computed using difference between the iterate xk and the inertial step wk, as well as the difference in their images. So we observe that it may limit the impact of the inertial step in some senses. So instead of doing that, we give improved version of algorithm 1 and algorithm 2 by updating the inertial step after the first iteration, such that the search direction is computed using the difference between two successive inertial steps as well as their images. So instead of using xk and wk, so we are going to use wk minus 1 and their images. So this is the improvement we have in this work. So the difference is the previous work has to do with the xk and minus wk, while in this one we don't need that. In every iteration we have 2 inertial steps. Those 2 inertial steps will be used to compute the side direction, and we give our algorithm as follows. So the new work we have here is algorithm 3. So the algorithm 3, we touched the conjugate gradient algorithm with inertial step, which is shortened by CGAIS. So if we are given 2 initial guess, x minus 1 and x0, we initialize all the parameters here and we choose our alpha k very carefully, such that it gives us a better result. So at iteration 0 or step 0, we compute the side direction using the steepest descent, and we compute the inertia, which is x0 plus alpha 0, x0 minus 1. So we test the tolerance. By the time we test this tolerance, then we compute this trial point. After computing the trial point such that the step size here, which is eta k, will satisfy this inequality 10. Once we have that eta k that satisfies the inequality 10, then we compute this vk here. After computing vk here, if this is equal to 0, we have to stop. Otherwise, then we compute the next iterate using this projection method. So by computing this, we have x now. We have 3 previous x minus 1, x0, and x1. So using that, we are going to compute wk plus 1, which is equal to xk plus 1 plus alpha k xk plus 1 minus sk. So computing this, then we can now compute our search direction. So you can see the difference between algorithm 3 and the previous 2 algorithms is that here in the search direction, we use wk minus 1 and their images. You can see their images here. Here in computing zk here. So this is the improvement we have from the previous presentation. So we can see like this one is extension of what we have presented in, I think, last April, if I remember correctly, or February, something like that. So after computing all these parameters, then we test the stepping tolerance again here in step 1. So when it satisfies the tolerance, we say xk is the solution and the iteration will stop. Otherwise, then we continue the process iteratively until the stepping criteria is satisfied. So the next algorithm is algorithm 4, which we call Spectral Algorithm with Inertia Step. For short, we name it SAIS. So it uses the same parameter as algorithm 3 here. The only difference here is that we set beta k equal to uk, which is equal to 0. So by that, we have our, by definition of spectral algorithm, we have spectral algorithm here. So this is how we compute the spectral algorithm. So the algorithm 3 has to do with spectral conjugate gradient method, while algorithm 4 has to do with only spectral gradient-like method. So we have this following remark. We ensure that the denominator here is always positive. This will avoid the direction to be undefined at some points. And we have these parameters. This one is lambda k, this one is our theta k, define the algorithm, this is theta hat. So we ensure that these 3 parameters are bounded below and above. This is useful for us ensuring that our algorithm 3 and algorithm 4 is convergent. So we have this result. The first result is lemma 5. We show that if xk is generated by algorithm 3 or 4, then we are sure that this property 5 will be satisfied. And this property 5 is very important in the convergence of our algorithm. Then next, we have lemma 6. If all these conditions here stated, then the sequence dk, uk, xk, and wk generated by either algorithm 4 or algorithm 3, then we are sure that this 4 conclusion will hold. So this one we have shown that I did not put the proof here. So then the final, we have the theorem here that if all the conditions stated here holds and xk is an dk which is set direction as generated by either algorithm 3 or algorithm 4, then we are sure that this will happen, and we are sure that xk will converge to a point x hat for which omega x hat will be equal to 0. Remember, this is the problem we are solving. So after the analysis, then the next will be the numerical experiment to demonstrate the performance of the two proposed algorithms. So in the numerical algorithm, we demonstrate the computational advantage, and we compare algorithm 3 and algorithm 4 with some existing method, of course, with similar characteristics. So what we did here, we used algorithm 3 and algorithm 4 with their existing competitors to solve some, a collection of some monotone nonlinear equations. So we select some from the literature, we solve it, and we check some metric. We check how many iterations does each algorithm require to obtain a solution, and the number of function evaluation, the CPU time, and we even check the norm to ensure that it satisfies our tolerance. But by checking the norm, we have that if algorithm A, algorithm B satisfy the solution, algorithm A and algorithm B obtain the solution, the norm will tell us which one has a solution that is closer to the exact solution. As I mentioned earlier, in numerical algorithm, sometimes you might not get exact solution, so we resort to approximate solution. So when the norm is closer to 0, then we say what we have, the point we have is closer to the solution. And lastly, what we did in the numerical experiment, we modify our algorithm 3 so that it will be suitable to solve unconstrained optimization problem, and by that we can use it to solve problem arising from robotic motion control. So experiment 1. Experiment 1 here has to do with the first algorithm, which is algorithm 3. So we compare algorithm 3 with two algorithms. First, we remove the inertia in algorithm 3. That is the one we call CGW, or WOI means without inertia. So, and another algorithm from our previous work, which was published in the, I think, Mathematics and Application, if I remember, HSS. So we compared algorithm 3 with these two algorithms. We set the following parameters, and our stopping criteria has to do with this. Whenever the norm is less than or equal to 10 to is less than 10 to the power minus 6, then we can conclude that we have approximate solution. And we declare failure if the number of iterations exceeds 1,000 iterations, and this stopping criteria has not been satisfied. Then we say the method has failed. So we use this initial guess, 14 of them, and this second initial guess, we either use the same or we add, some constant to it, which we represent by I here. And we use a dimension, 5 of them, that is 1,000, 5,000, 10,000, 50,000, and 100,000. So for experiment 2 here, we test this algorithm 4, which is the spectral gradient like with Inertia Step. So we test it with our previous work, which was published in the IEEE Access, which we call DAIS1 and DAIS2. So because this DAIS1 and DAIS2 have also Inertia Step in them, but as I mentioned earlier, not like this. In that one, it uses difference between the point and the inertia and their images, while the algorithm 4 here uses difference between the two preceding inertia. So this parameter also was set, while the parameters for this, we take them from the work in IEEE Access. So this is the graph showing the performance, and this graph was prepared by the aid of Dollar Ammo Performance Profile, which I'm sure many of us in this forum are familiar with it, because we have presented many work using this performance profile. So this is the first one, algorithm 3. This is CG without with inertia, that is the red color, and without inertia, this is blue color. So you can see the impact of the inertia, because the only difference between the blue and the red is the inertia step. So we ran the experiment and we found that, yes, incorporating the inertia actually improved the numerical performance. While the best one here, that is the red color, then we now compare it with our previous work, that is HSS, and we can see still it's better than this. HSS has no inertia step incorporated into it. It's just a simple, a normal algorithm where we use only one initial guess. So this is a performance profile with respect to the number of iterations for algorithm 3. Then the next one is the performance profile for the algorithm 4, that is the spectral gradient with inertia step. So we compare it with our previous work, DAIS1 and DAIS2. So we can see from the graph that based on the number of iterations, our algorithm performs better than the two existing ones. So the next one is the application. As I've said earlier, we try to modify algorithm 3 so that it will be suitable to solve this type of problem. That is unconstrained minimization problem, minimization of f of x such that x is in R. Sorry, x here is in R and not R plus. This is a typo. So this function here is assumed to be continuously differentiable, and of course the function is also assumed to be convex. So by modifying algorithm 3, this is what we do. Remember, omega here, we take it as a function from Rn to Rn, which we use it to define our nonlinear system of equation. So, but in this algorithm 5, we take omega here to be the gradient of this real value function. Remember, f is from Rn to R. So when we take its gradient, then the gradient will be a vector value function from Rn to Rn. So we can view this, we can take our omega to be equal to the gradient of this. So this is the first modification. While the second modification has to do with the way we compute the step size, that is the step length. So we use this line search instead of the one we use in algorithm 3. We change it to give us this, because using this, then we are going to have our convergence analysis easily. While the third modification is that we did not use projection here. We simply compute the subsequent step using this. And of course, we even set alpha k equal to 0. By this, we don't even need the inertia here. So to ensure that algorithm 5 here is converges, then all we need to do is we assume that this level set here is bounded. If this level set here is bounded, here we said f is continuously differentiable and f is also a convex function. These three conditions is the condition that theorem 2 of Sun et al. Has to satisfy before we have convergence. So when we have all these three assumptions at hand, then we can guarantee that the lim inf of this will be equal to 0, and that shows that algorithm 5 actually converges. So after that, then we now describe our the experiment or the application. So it goes as follows: a discrete time kinematic equation for robotic motion control experiment. All we need to do, we have to solve this minimization problem. This is this unconstrained minimization problem, f of q, where of course our f of q is nothing but this least square problem. So we solve it at computational time interval tk, which is in this. Tf here is called the final time, that is the duration of the task. So we have qdk here is the n effector control track. So what we need to do here is we allow the n effector here to the n effector here is controlled to track the following Lissajous curve. So we have two Lissajous curve, which we call q1 dk and q2 dk. So for the length of the rod, we take L1 and L2 to be equal to 1. We have all these parameters here, and we divide t here into 200 equal parts, where of course tf, which is the duration of the task, is given by 10 seconds. So using this, we run the experiment. So if you look at the graph here, we have this blue one is the desired path, while the red here, I think it is red, so it is called the actual trajectory. So what we need to do is we want our algorithm to track this desired path, and by merely looking at the graph, you can see that the algorithm successfully, performed the task given to it. So this Lissajous curve is calculated or is done using this QDK1, which is 3 by 2 plus 1 by 5 sine of 3k. While here you can see there is no 3 here. This one, I think the only difference is this 3 here. So, but removing 3 changes the track we are going to follow. So these are the error. You can see because we set the tolerance to 10 to the power minus 5. So this is the error we have in doing that. So the second Lissajous curve has an infinity shape. That is the QDK2 given in the previous slide. So you can see the blue one here is the desired path, while the red one is the actual trajectory. So we succeeded, our algorithm succeeded in tracking, in following the path here. So also the error recorded is almost flat here. You can see 10 to the power minus 5, that is the tolerance we set. So basically this is what we have in this talk. And I thank you for your attention. Now, Woody, Kopunka.